Okay. And then we have another post about verification of participation, right? The registrar's office asked each one of us in the second week of the semester to start reporting students' participation in the classroom. And there are different ways how we do it. Our first homework is due after the deadline for VOP. So I put this poll and survey, which really helps tweak the material as we go along the semester. So please make sure you fill out the survey before next Wednesday. So Wednesday night, I will submit my report. It should not take more than 10 minutes. It's just 8 questions, nothing really, nothing technical. Any questions so far? Okay. So let's just have a recap, and then we start looking at logistic regression. Logistic regression, we will look at it today, and then we will revisit this in a couple of weeks when we talk about the regression as an application. Okay. So we're still in the classification kind of chapter. We are still in the middle here looking at different classifiers, and we will move by next week to finish up the problem. So what's the classification problem? So now, if we have a one-dimensional input, basically your input is just a number, right? So now on the x-axis, we have these different inputs. Then now your boundary, your decision boundary, just will be a single point, right? Just a single point. You say basically to the right in here is 1, for example, to the left is a 0, right? So your decision boundary in this case is just one point. So you can really look at your output as y as 1 if you are really higher than that decision boundary point, and then 0 if you are on the left-hand side or smaller. If it's two-dimensional input in this case, then basically your decision boundary is nothing but a line. So you have x1, you have x2. You can think of these are coordinates, are two features, like you describe your data with two features, x1 and x2. Then basically in that case, you can really decide on which one belong to first class, which one was the second class, using a line, right? So you can really draw this line in here, and then basically anything on this side will be a 1 in the output. Anything on the other side of the line will be a 0. So that's basically kind of what really a decision boundary looks like. In both cases, the output will be something like in the y equal to 1, and then after that, after the decision boundary, the y equal to a 0. Same thing in here is easier to look at it. You have 1, and then drop, and then you have a 0. So this is a special kind of shape that we will look at in a minute. Okay, so this kind of table that kind of compare the different algorithms in a classification in a matter of different factors. What we have on the left-hand side, the different algorithms from logistic regression to the KNN, decision tree, SVM, naive Bayes, and then ANNs. And then we have these different factors. The first one is, do we have any assumption about the feature distribution, or distribution of the features? And I just am highlighting the two algorithms that we discussed last time, the KNN and the naive Bayes, right? So in the KNN last time, we didn't really have any assumption, right? We didn't really impose any requirement on the feature space, right? However, in the naive Bayes, we basically said, okay, it's where the need is coming from. We are assuming that the data is independent, right? The input data or the features are independent of each other, which is not realistic for real life data. That's one of the shortcomings of naive Bayes, right? So then the next column is, do we really require normalization, right? And we had an example last time when the KNN basically, without normalization, there will be a bias to one feature compared to the other feature, right? So basically, it makes more sense to have a normalization. It will make your data less biased to one feature over the other. We didn't really have that requirement for naive Bayes in this case. Cost function, neither of them really required. Although, I mean, you can argue, or some could argue that the distance that in KNN could be viewed as a cost function. But the cost function here, it will be more obvious when we talk about regression and then later on ANNs. But in that kind of definition is not really required for these two algorithms. Again, regularization, we haven't really discussed that yet. Hopefully we'll have time to talk about it today in the logistic regression, but we don't really have any requirement for that in the KNN or the naive Bayes in this case. Is it linear classifier or is it nonlinear classifier? So the KNN is nonlinear classifier, right? The naive Bayes in here, it's nonlinear. And then in the next homework, I will hint to this at the end of the lecture today. But the next homework, you will look at this. You will derive the naive Bayes for Gaussian. And in that case, basically, we have a linear classifier, a special case of naive Bayes. Do we have a probabilistic view of prediction? We don't have that in KNN, but we do so for the naive Bayes. The whole idea is the Bayes rule and come into the picture, so we can estimate the posterior probabilities in this case. And then in a minute, I will talk about what we mean by generative compared to discriminative classifiers, and then what is really parametric compared to non-parametric in this case, and then overfitting. So in overfitting, if K is really very, very small compared to, and that small, it depends. Like if it's 1 or 2, then it's really, we have overfitting, but it depends on the data itself. But usually if K is small, then we have overfitting in this case. In the naive Bayes, we don't really have that problem in general. So now, parametric modeling compared to non-parametric modeling, this is basically something we'll keep seeing throughout the semester. What we're really trying to do, we go from the input data in the feature space X to the output. In this case, is the classes 0 or 1 for in the binary classification. And then we have a parameter over a parametric model, which is we'll describe as theta. So if we really have a certain parameters that we are really trying to calculate or estimate, so that will take this mapping from the input space to the classification or output or prediction output Y, then we have a parametric model. Naive Bayes is one, logistic regression is another one, MLP and ANNs and the SVNs are all parametric models. And generative versus discriminative classifiers, the easiest way to look at it is what you have on the left-hand side. I will leave the rest for you to read at home. So it's all about, are we really, are we generating basically this model and how we are really learning it? If we are modeling the posterior probability directly, right, to learn, then we have discriminative classifier. If we are indirectly estimating the posterior probabilities, like in the naive Bayes rule, for example, then we are having a generative classifier. You can think of it basically, we are really generating these models before we really estimate it indirectly. That's not the case in a discriminative. So you can think of the KNN, for example, a discriminative because we're looking at how we can really discriminate between the different data. We will keep looking at this throughout the next 3 lectures, what it means. And in many of the slides, they are really more lecture notes. So I will not go through everything in the slide. So I will leave the right-hand side for you to read at home in this case. But in any case, so we will stick to this table in here just to put things into perspective. I think it's a good idea just to keep this in front of you while you are talking about classification and homework too, especially because it will make things a little bit more, hopefully clearer in this case. Okay. So let's jump into the new topic of logistic regression today. And then this is really nothing but a probabilistic classifier. It really directly estimates the posterior probabilities, a probability of Y given X. And then the key terms are sigmoid function, the weights, and the bias. And we'll look at those in a minute. Okay. So if you look at this problem in here, back to what I started with, and the easiest way is to look at the one-dimensional input. So this is one-dimensional. You have a boundary point. Like so, the boundary decision boundary is just a single point. To the right is 1. To the left is a 0. Right. So this shape in here, that's what they're really interested in this case. We have that shape of a function that will give us basically what we have on the right-hand side. We have 1 at a certain point, and then 0 after a certain point. And then for now, it's just the easiest way is just to look at this as one-dimensional data input, just for the time being. Now, this is really a special function. We call it the sigmoid function. The sigmoid function, sigma of x, is 1 over 1 plus e to the negative x, where x is the input. So if it's really a single, the one-dimensional, then it's very obvious, especially that at a certain point you have y equal to 1, and then before that is y equal to a 0, 1 over 1 or 1 over a large number, which is a 0. So as you go to negative infinity, this becomes very large. This becomes equal to a 0. If this becomes really very large, this point will be a 0. 1 over 1 plus 0 is 1. That's why we have the output in here. So this is the sigmoid function. Right? So now what we are really modeling in here, we are really not inputting x. We are inputting the weights times x plus b. Basically, the easiest way to look at this as you have your weight function. So you have 1 So this is P by P weight function, and then you have your X. So this is X1, X2, all the way to XP, and then plus the bias that we have in here, B1, B2, all the way to BP, right? So basically, that's basically what we are looking at. We are estimating, we are trying to figure out what the weights are, because at the end of the day, we are trying to do, in the simplest way, W1 times X1 plus W2 times X2 plus W3 times X3, all the way to WP times XP plus the bias, and that basically becomes your function. We are estimating what these linear combinations, these linear weights, right? And then this one, the bias in here. So that's what we are really trying to estimate. What are these weights that we are really trying to, away. Good. Okay. So, and basically that will be our linear model for what these weights will be to maximize basically the output, to minimize the error in the output. Okay. So now the easiest way to look at this, we can say, let's say just look at the least square cost function, meaning that I'm taking my prediction output, right? Imagine you have data, you have the output for that data. So you have now, these are unknowns, the W's are unknowns, the B is unknown, you have the input X, right? How many of them? You have capital N. So you have N of these input data, right? And then now for each one of them, you have a prediction. Imagine that you can find what these weights are, right? Minus the true prediction. So this is really the true value. This is the ground truth, right? So this ground truth one could be a 0. So if what they're trying to do, we're really trying to minimize the difference between these two, right? The prediction output on the left-hand side and the ground truth output on the right-hand side. This is the ground truth that we have from our data. So this is the least square. We take basically the difference. This is the minimum square error optimization. Basically, we take the difference square, average over all samples that I have, N of them, capital N of them, these input samples. And then in that case, if we replot that plot, it will be something like this, right? So this is an non-convex function, and there are really many local minima. So this is very, very difficult basically to find a global minima in this case. So basically the least square or the minimum square error solution in this case is problematic. Any question about this model? Yes. What's it again? So basically what we're trying to do, if you're really minimizing the error, you want your function to be like this. So this is basically what the minimum is, right? And I think I have, yeah, this one here, for example. So this one here, imagine that you have a cost function, you have your input parameter theta. Theta is nothing but W and B, right? So now this is basically a convex. Basically, in that case, you already have a minimum, and here you're trying to get to that minimum, right? In that case, when you really model the problem as a least square problem, meaning that take the difference and square average over all samples in the input data, then basically what you have in here is a non-convex problem, right? So that's very difficult to find global minima, because it's very easy for you to really hit the local minimum, and that's not really the optimal or quasi-optimal solution in this case. Another question? Okay. So now that's given. Now what we have in here, really just remember what we have. You would like to have a function that really looks like this, that the sigmoid function. The parameter is X, so this is X, right? The next thing is you would like to take the X in here and map it basically linearly, right? Now we have the weights and the bias. So we have the weights times the input data plus B. Remember, this X1, maybe I should have done that. So X1, 1, X1, 2, X1, 3, X1, P, right? All of these, right? X11, X12, X13, all the way to X1P, these are the features for my one input sample, right? See that? So I have, this is my input X1, and then I have it is represented by X11, X12, all the way to X1P. That's my feature vector for one sample, right? Now, how you decide on this feature vector could be 1, like the length will be 1, 2, or P, or 100. It depends on the problem that you have, right? So you will see that the last problem you have in the homework, the new homework, we have the iris, And you'll see basically with how many features, how many features we have. That's P, right? Capital P in this case. Any question about this? So now for this sample, I'm finding I can describe my sample using these features in here. I'm trying to find a combination, a linear combination of these features that will give me basically, is this a 1 or is this a 0? Right? That's my classification output. Right? That's what I'm trying to find. Does this make sense? Don't lose the big picture of what we are trying to do in here so far. Any question about this? Now I go to the next sample, and then I have W1, I have X21 plus W2, X 22, all the way to WP X2P, right? Plus P equal to what? Is it 1 or is it a 0? But now I have the weights are really kind of, and now you can imagine I have n of these equations, right? I have capital N of these because I have n samples. And then I'm trying to find the solution, which is what are these weights and bias? Okay, that's basically what we are trying to do. Yes. Let me break this down and then. Good. I don't know how can I bring this down further. I'm not using it. Oh, good. Okay. I need that one though. So okay. So now that's basically the setup that we are trying to do in this case. Are we good on this part? And now why we cannot use the least square solution, right? Or the minimum square error solution, because it's not really a convex function. Okay. So now let's move to do this in a different setup. Okay. So we established that we have this sigmoid function here. We have this feature vector, right? So for our input sample, x1 through xp transpose, because we're looking at the column vector. What we're trying to do, logistic regression, we try to model the probability with a sigmoid function, meaning that the probability of y given is equal to 1 given my input x is really nothing but the sigmoid of the linear combination of my input data. Why? Because the sigmoid function here, if it's y equal to 1, then I am trying to, this is sigma equal to 1 here. If it's y equal to a 0, then I want to be here. So it makes sense to model this using a sigmoid function. So you're really trying to figure out this conditional probabilities for y equal to 1 given x, given basically these weights. Okay. So now, but keep in mind that also we could really have probability of y equal to a 0 given x, and then the combination of these two will be equal to 1. We have only two possibilities. This is a binary classification where the output could be 1 or a 0. And later on, we'll talk about when the output is 1 or -1. Is a different soft plus problem we'll talk about later on. So for now, it's 1 or a 0, right? The binary classification. So now in that case, what we have, the probability of y equal to 1 given x could be a sigmoid. The probability of y equal to a 0 given x is 1 minus that sigmoid, right? That's basically what the modeling will look like. The classification rule now, the output will be equal to 1 if that probability of y equal to 1 given x is larger than or equal larger than 0.5. It will be equal to a 0 otherwise, right? So this is why, actually, to be more accurate, later on we'll talk about this as y hat. That's my prediction of the output in here, y hat, not really y. Y is the ground truth in this case. Are we good with this model? Okay. So now let's see how we can. There are two different ways how we can really set up what the cost function looks like, right? So now imagine that this is just, we'll name this as conventionally done in the literature, this sigmoid function as a z, right? And usually this z is really for a certain input. So usually I have x sub I, and this will be z sub I, right? So that's for a sigmoid output, right? What I'm trying to find out is the following. If my output is equal to 1, right? Then I would like to have a cost function. This is a cost function. In a minute, you will know why it works. LL is the cost function. What is really the input to the cost function? Is my z, the sigmoid, right? So now, in this case, I want this cost function, right, to be equal to a 0 if the out of the sigmoid is the same as the input, right? That means I have this correct, right? If it's correct, that means I really don't have to pay any penalty. It's 0, right? My penalty, my cost value is a 0. Does that make sense? Okay. However, my ground truth is 1, right? If the out of the sigmoid, which is z in this case, is really approaching 0, means it's really very, very small, right? That means I really have to penalize. I have to pay quite a bit of penalty. Is infinity in this case, a very, very high cost for in this case, and vice versa, right? If I y equal to a 0, then my penalty or cost function will be a 0. If they're equal, it will be very high if z goes to 1, right? You can plot these here, right? So what I have on the x-axis is z, and here, this plot in here, when y equal to a 1, as z approaches a 0 in here, then the penalty or the cost is very, very, very high. As I approach 1, the penalty will be 0, right? Very small. And vice versa. If y equal to a 0, again, I have z in here between 0 and 1. This is my cost function. If it's z equal to a 0, because y is over 0, then I should not really penalize myself. So this should be a 0. As basically z approaches 1, then I have to pay quite a bit of a penalty. The cost function or the cost is very, very high. Does this make some sense? Yes. We are trying to figure out what that cost function is. We are trying to calculate that. A cost function means, remember, when we have at the concept level, we have this combination, right? We don't really have these weights. We are trying to find the way to calculate these weights, right? From the easiest way to say, I will take basically whatever the output of this one. Like I will go through, like an infinite combination of what these W's are, right? Why not? I just want to go brute force on all the values of W, right? You can make it very simple to say, I just have 2 weights. W1, I have x1 plus W2 times x2 plus B. And then this is basically my function, right? I'm going to find all the W's, right? And the B that will make basically this give me the correct output, right? So now what will that be? I could say I would like to find the sigmoid. Let's just call it Z. Zi minus Yi, right? That's the difference, right? This is the model, right? This is Zi, right? This is the sigmoid of this. This is my Zi, and this is I1, I2. You see that? So this is the linear combination, sigmoid, that will be my Zi, right? I want this Zi to be equal to the true output. If Yi is 1, I want Zi to be equal to 1. If Yi is equal to 0, then Zi equal to 0, right? So I have this error here. So now I need to find, when I solve this, I want to solve this I want to find the weights for all the possible capital N samples I have, right? So I have N of them. Could be 100 samples, could be 10 samples, could be 1 million samples. So now I have this kind of huge, basically, system of equations I would like to find these W's from. So now I have to minimize this error. So now I need to go to my optimization literature and see what I could do, right? The easiest, or the first one, I take the difference, square it, sample over all my N samples, right? And I want to minimize this error. And I have an optimization solver, and then it will bring me back what the W1, W2, and the B should look like. Does that make sense? So now that's what I'm trying to do. So now we saw this in here. This is non-convex. It's very, very hard to find the global minima. You will always hit the local minima. And imagine this is in here, capital N. Could be in the millions, could be in 1,000, could be in hundreds, right? It's very, very large. And the P, the dimension, capital P, how many features for each sample could be also very large, right? Not necessarily small though. So now that's what I'm trying to find. Now, the next thing is, let's really try to figure out a different way how we can do this minimization. What's the minimization? I'm trying to find, I want to minimize some function, right, of this difference. I want to find how I can minimize this difference, right? So that's my ultimate goal, right? So now one way to do that, this is just to go back and look at the setup of the problem, right? And one way to do that to say, if my true output is 1, then my cost function, because what is my cost function in this case? Is the minimum square error. Diff error square average, right? That's the least square, right? We know that this is really not a good solution because it's not complex, right? Now we are trying to say, okay, I want to find what should be the characteristic of that cost function, right? So now when y equal to 1, I want my cost function, which I don't know yet, to give me an output of 0 if the prediction is equal to the ground truth, right? That's my constraint on the cost function. At the same time, if my true output is 1, but my prediction is approaching 0 or is equal to a 0, I want the cost function to give me very, very, very high cost, very high penalty I have to pay. Does that make sense? And you can do the same argument when your ground truth is y equal to a 0, then you can really look at the same characteristics of the cost function. Does this make sense? What the cost function is? Okay. So now we plot these in here, and you can tell right away one function that can describe this cost function here is basically the log function, right? So the negative log. So now when y equal to a 1, right? Basically, if you don't really have this log, then it will be going from negative infinity all the way to a 0, right? Take the negative, then it will be something like this one. So this one here can be described using this function here, right? But that's condition. This is a function of z, and the condition here when y equal to a 1. So now my cost function could be a negative log of the z when y equal to a 1. And similarly, I can really describe this using a log as well, which is log 1 minus z with a negative because now I'm going up when y equal to a 0. Okay, so that's one way to describe our cost function. Any question about this? Okay. Yes. Yeah. For now, yes. Yes. Okay. So now this is one model, which is really the very simplified, naive way to look at the problem. So now I have this cost function, but now I want to bring it into a closed form solution. So now the y equal to a 1, I want to bring this into the log, right? So now I can bring that here. So I have y times log of z. And then I want to bring the second one when y equal to a 0, 1 minus y times log 1 minus z, right? That's one thing. So now when y equal to a 1, I have this one here, this term. When y equal to a 1, this will disappear. So I have the first part. When y equal to a 0, this will disappear. And then I have 0 in here. That's been 1 times log, which I get the second term, right? The second thing I'm doing in here, my cost function should be really a function of all the samples. So now I'm averaging my cost function over all samples, n of them in these samples, and the negative from here. Okay. So now I'm putting together my whole cost function for all samples, right? There's all samples in here, right? And then I have, that's why I have this index I, which is for the sample number, right? Yes. No, z could be any value, right? The way we are setting it up in here, you're looking here. So it could be really very close to, not necessarily equal to 1 or 0. It could be very close to 1 or very close to a 0, or in between, right? So we don't really have any constraints on that in here, right? Because if you go back to how the sigmoid looks like, this is how it looks like. It can be any value in between these ones. You see that? So now how we map it, basically, the input to it, the input will be any values, the output will be anything between 0 and 1. That, right? And now we're really trying to find what is this decision boundary, right? Where we can classify as 1 or 0. Okay. So that's one way to look at this setup in here. Another way to look at this one, using Bernoulli distribution, right? So if you look at the probability mass function for Bernoulli distribution, it's the one we have in here, right? p to the k, 1 minus p to the 1 minus k, because I have only either 1 or 0 as output, right? That's Bernoulli distribution, right? I have 1 or 0 as the output, so I can have describe the mass function as basically p to the k, 1 minus p to the 1 minus k in this case. So now in this case, I have the k in this case could be a y, right? That's my output, right? It could be a 0 or a 1 in this case. So I could really write that as something to the y, 1 minus something to the 1 minus y, right? That's my output. Again, what is that something in the middle in here? I'm sticking to this sigmoid because that's how the problem is really laying itself out, right? It's a sigmoid function, right? So now I'm still sticking to this sigmoid function here, and then I have to the y, and then 1 minus sigmoid function to the 1 minus y in this case. And again, if you take the log of that, then I have y, because it's exponent, will become in front of the log, so y times log of sigmoid, which is z, plus 1 minus y times log of 1 minus the sigmoid, which is z in this case. And now, either we are really maximizing this, right? Or we are really minimizing the negative log likelihood. And that's basically where the capital LL coming from. This is the log likelihood in this case, right? So either we are maximizing this or minimizing the negative log likelihood. So if I multiply this by negative, then I will have minus y log of z minus 1 minus y log of 1 minus z, which is exactly what I had before in here, right? I could now really sum this or average this over all my samples. I put y sub I have x sub I, yi, sigmoid of xi, yi, sigmoid of xi. Okay, yes. Yeah, I mean, we are sticking to this throughout the semester. The out of the sigmoid is just z. It will be easier when we take derivatives. Yes, yes. I mean, that's I should have it somewhere. Let's see if I have it. Yeah, here. Yes, it's here. See that one? Right. Now, if you are looking at just a single sample like xi, then this will be zi, right? And then you will see basically throughout the semester we try to find for linear algebra, just put everything into matrices and then just operate in the matrices overall, not on an individual sample as we are doing in here. Exactly, exactly. When you move to the neural network side, we just look at it as a matrix, as a matrices. It will be easier to look at that. Okay. Okay. So this is basically kind of putting all things together. This is the end of the day, what our cost function looks like. This is the LL for log likelihood. So we're really trying to look at the negative log likelihood cost function, and it's really a function of my input samples xi's, my true outputs yi's, and then remember the sigmoids in here, they have the w's and they have the b's, so they have the weights and the biases in this case. So this is in here, this cost function here, we refer to it as the binary cost entropy cost function. Okay, this binary cost entropy cost function. And I don't think I'll do that today, but later on maybe I'll just bring back where the entropy coming from in this case. Any questions so far? Is the cost function clear now where we started? So now this cost function here and here, this one here, it's just by looking at it from here, right? It has convex. It has a minimum, right? A global minimum, right? That's what we're looking at. Not like the least square solution that we had before. So now the next question is, how can we solve this problem? And this is really the problem. The problem in here is, how can I find the minimum, right? Because remember, either we are maximizing the log likelihood or we are minimizing the negative log likelihood, right? So we are minimizing the cost function. What will be those parameters? So now we refer to theta as W and B. Usually, this setup in here, the way we do it, we add a column of 1 in here. We add a 1 here. Right? Sorry, this is B. This is B, B1, B2, all the way to B, P. We add a 1 here, and we get rid of this part. Right? It's the same. It just is much easier. So now this whole thing in here is basically our theta theta model. Okay, so theta model is really the W's and the B's. Okay, it could be theta I, that's basically what will be the weights for that particular sample, one sample. Okay, so now this cost function here, it looks something like this. Remember when we derive this when y equal to 1 or y equal to a 0, right? So if you look at, in this case in here, the derivative with respect to the theta, the model, will be positive. When you are in here, the slope will be negative, right? This is the derivative of the loss function, LL with respect to theta is negative, and here will be equal to a 0, right? So now, usually, when you take a derivative for a certain sample, you are really here, right? At a certain, for example, you are here, right? What you are really trying to do, we're trying to do an iterative way to get all the way to here, right? So now you start to say, okay, now I have this iteration that I have to really go through, which is the gradient descent algorithm. But now, ideally, I wanna be here, I wanna jump here, jump here, jump here, and now I'm at the local minimum. I'm at the minimum, right? So that's my solution, right? But in many cases, it could be, in some cases, not many cases, I'm here, I will bounce here, I'll keep bouncing, right? So now that will be a problem. I will not converge to the solution quickly, right? That's my learning rate, right? What's happening. So we'll look at this in much more detail throughout the semester. So now, what is the gradient descent algorithm? Let's take a detour to calculus, okay? So our x basically in there, I added the 1, same as in here, right? So I added the 1s in there, so that my theta has the b and the weights, and now I can really write this whole thing as theta transpose times x, right? So theta transpose times x, right? Right. So they're just I'm trying to just simplify things. Now again, I want to write this theta transpose times x as an h, and then sigmoid of the wtx plus b is nothing but really the sigmoid of theta times x, which is nothing but the sigmoid of h. So I have 1 over 1 plus e to the negative h, right? I'm just trying to have a nested way to apply the chain rule later on, take derivatives. Okay? So if I were you, I would start to write basically, start from w transpose times x plus b. That will be equal to theta transpose times x, and that basically will be equal to h. Sigmoid of h is really equal to a z. That's basically kind of the 4 nested things that we are looking at. Okay, so now this is my cost function here. Nothing really different. And let's look at the chain rule. So we have the partial derivative of my cost function with respect to the theta. Because at the end of the day, I'm trying to find my solution. This is my solution. This is the unknowns. I want to find what would be these combinations in here that will give me the minimum cost function, the minimum value for this, right? So that's why I have theta in here. But I have a chain rule, right? So now if you look at the theta, if you look at, it's really a function of, h is a function of theta. So now I have partial derivative of h with respect to theta. But the h in here is part of the sigmoid. So I have the partial derivative of the zi with respect to hi, and now I have the partial derivative of the cost function with respect to the zi. So I have this translated to 3 terms from the chain rule. Any question about this? Do you see that? Why we are doing it this way? It will make it easy just to calculate what will be this value, what will be this expression, what will be this expression. Okay? Now, let's look at the first one. I'm taking the cost function with respect to the zi. What is the zi? Is this one here, right? This is zi, this is zi, right? Now, apply basically the derivative. So I have yi, derivative of the log in here is what? Is 1 over zi, right? So I have negative in here. I have yi over zi from the first term. From the second term, I have 1 minus yi. Derivative of this is what? 1 over 1 minus zi. So I have 1 minus zi. And then the 1 minus yi is this one here, but because of the chain, I have a negative one here. If I by a minus sign, this will become a negative. This plus will become a negative. Do you see that? Okay. I can just rearrange term. I have it in this form. Any question about this? Simple calculus. Any question about it? If you just do it at home, I mean, it's straightforward. Now, the next term, I have the sigmoid. The ZI is my sigmoid. It has a very specific feature, and we'll revisit this in the neural networks as well in the back propagation part. So partial derivative of ZI with respect to the HI, right? What is my ZI? ZI is 1 over 1 plus e to the negative HI, right? So now, you take that derivative in here, and there are multiple ways how you do it. I think you'll derive this in the second homework. But basically, you have 1 plus e to the negative HI to the negative 1. Then basically, what is the partial derivative with respect to the HI? This basically will be what? This will be negative 1 plus e to the negative HI, negative square. Then what will be the derivative of this one is times minus e to the negative HI in this case, right? And then take this down, just do some operations. What you will end up with, this is very, very well known for the sigmoid a feature of the sigmoid function. The partial derivative of the sigmoid function is the sigmoid times 1 minus the sigmoid. Right? Remember this. We'll look at this in back propagation later on. So a partial derivative of the sigmoid function is another sigmoid times 1 minus the sigmoid. Right? This is a very important feature of the sigmoid function, because that will give us in the back propagation, the neural network, that nested calculations later on. Any question about this? So this is the second term in our chain rule. So we finish this one, this quantity is this one here. And then finally, we're going to find the partial derivative of HI with respect to the theta. But basically, this is nothing but very simple. So I have H equal to theta transpose times X. Partial derivative of this with respect to the theta is nothing but the X. Right? So for an XI as an XI. Okay, any questions? Okay. So now I can put all these things together, take this times that, right? And then plug them back into what we have in here. Then I will end up with this update, right? So my partial derivative of the cost function with respect to my parameters theta, which are the W's and the B, is nothing but basically the sum or the average of yi minus the sigmoid times the xi average over all my samples. That's my cost function in this case. The derivative of my cost function with respect to the parameters. Now, in the gradient descent, this is the update, right? This is basically how much update I have. So I start from here, right? And then now, what will be my update if I change my parameter by this much? I'm jumping here, I'm jumping here, jumping here, jumping here, right? So now these jumps, how do I control these? It depends on how much update or weight to the update you wanna impose, right? So at a certain iteration, t plus 1, I'll look at my parameters. This could be some initialization. I mean, that could be, but or the middle of the iteration. On update with this quantity, and now I want to impose this learning rate, right? How much weight I already, how aggressive I want to be. Do I want to be very, very aggressive, or want to be very basically conservative in terms of how much update I want to impose in here, right? We like to put everything into a theta, but you can really look at this when you do the calculations basically in your homework. Either you look at this as a theta, or you can look at this as W and B. So, and you look at these as two separate quantities. So either you do this, or you can do these two equations all together, and they are the same. We'll give you the same update as you go from one to the next level. So now this alpha in here is our learning rate or step size, how much aggressive we're going to put. And this in here is what we call it a hyperparameter, meaning this is something you want to try. Basically, depends on the data, depends on like the features. You want to be aggressive or not, it depends on how you really. That's where babysitting the learning algorithm, right? You just try to different alphas and see basically how the learning curve. And you will do this in the second homework. You will do different ways of how you can really come with a feel of what alpha should look like. And usually it's 9.5, usually. in this case. Any questions so far? Okay. So now one more thing. Remember when we in the KNN we did normalization, min-max normalization for the data input data. That's very, very important for the gradient descent. So now if you look at with that normalization, this is our cost function. These are the number of iterations, right? Start from the initial case, and then as you really update, keep updating, you can see basically you are not really, you're jumping around, right? That normalization. When you do normalization, you're converging very, very nicely, right? Right. So that's basically is almost like the first line in your code, it will be just normalized, right? It's nothing that will not hurt, right? So always normalize. Just keep that in mind. And I think there's a very small sub problem in the next homework where you do this experimentation and see it in front of you. Okay. The second thing we usually do, it stems out from this problem, right? And this is something I always tell my students. I mean, machine learning algorithms, neural network especially, they are very, very lazy, right? If there is a shortcut to find a solution, they will do it, right? Even though it doesn't make sense, right? But they are very, very lazy. And this is true. And here, what will be, if y equals 0, my output is equal to a 0, what will be the best sigmoid, right? Then the algorithm will try to maximize basically to get to the solution very, very quickly by making the parameters really very, very, very large in the negative sign, right? Because 1 over 1 plus e to the negative hi, right? So basically, if I want to have that one to be equal to a 0, then I'll make the denominator very, very large. Then the hi has to be very large in the negative sign, right? That's the solution. I'm getting a 0 output, right? And vice versa, 1 over 1 plus e to the negative h. If I make basically the h is very, very, very large, then I will have 1 over 1 plus 1 over very large quantity. That's 1 plus over 1 plus 0. That's 1. And it will give me the solution, right? That's overfitting, right? This basically, the algorithm will just very quickly say, yes, the parameters are really, make them very, very like large in the negative direction or very large in the positive direction, depending on the output that you want. That's an overfitting. That's a problem with just leaving it like that. One way to really mitigate this issue is what we refer to as regularization. In a nutshell, what we're trying to do, this is the cost functions we have. We would like to regulate basically what output will be, what the parameters are. We are really trying to limit, right, the values of our parameters data. We don't want it to be very, very large, either negative or positive, doesn't matter. That's why basically we have the L2 norm of theta. Forget about this, but we'd like to minimize this. But now we are adding this to this theta, L2 norm of theta. We are minimizing this whole thing, right? So now the solution, although I'm trying to push very hard to make this theta very, very large, but really you are telling them the larger the theta, the more penalty you will have. So now that solution will not be that trivial solution. Do you see that as the regularization or regularization of the gradient descent algorithm? Any question about this? What you're trying to do? Yes. Overfitting, basically, you are trying. So in general, we are really trying to find these things in here, right? That can be general for any data, even the ones we don't really have in the N samples, right? So now, if your solution can only work for your N samples, but when you have a new sample, it doesn't really work for it. We call it basically this is not generalizable, right? That means your solution is overfitting to your samples, right? Right? So now, in this case, in this scenario, is even overfitting is much more specific. The solution is trying to really overfit, basically find your model specifically to this case, right? When y equal to a 0, right? But now theta will be negative infinity, right? But will this solve the problem when y equal to 1? No. Even within that problem, it doesn't really work. So your model works for only one case, but not the other case. What you are trying to find, you are trying to find these weights and biases, right? That can fit basically, it doesn't matter what the output is. You want to find the predicted y to be as close as possible to the real solution, right? for any sample within the domain, right? Not only the training samples, right? So are you fitting the solution to what you have as an input, right? If you are really customizing it just for that input, then you are memorizing. You're not really doing any learning, right? It's only memorization, right? And that's definitely not something we want, right? And that's basically kind of this overfitting to is really kind of to find a trivial solution. We can really mitigate the problem by adding this term in here, which is the regularization term in this case. Okay. So now, this is basically we are really, since we have the L2 norm for our theta, we are really averaging over all these in samples because we're doing this for all samples. And then I have this lambda in here. This is basically another hyperparameter. And that basically hyperparameter in here, it gives me a trade-off between how much I want to add weight to this term compared to this term, right? Right? How much I want the algorithm to go nuts, like to really go to the very large values. Do I make this space lambda very, very small, or I want to make this lambda a little bit high in this case? Again, this is another hyperparameter where you depends on the data, the problem, you will see basically how much convergence you will have and how much generalization you could have. Any questions? Yes. We will talk about that, right? It's basically linearly separable data, right? For linearly separable data, yes, right? And we'll see how we can use for nonlinear separable data, right? Where? Because it's already there, because the L2 norm, right? So this will be the square, right? Yeah, right? That's the L2 norm there. And then later on, we'll talk about the neural networks. Then we'll look at different regularization parameters. For now, I'm just introducing what regularization is, but later on, we'll look at this in much more depth. You can use L1 norm and some other norms. Okay. Okay, so now, I know many things. If you haven't seen this before, I have sigmoid function. And then how we can really set up the problem to make it. Set up the problem. Wait, hold on, just summarize. Set up the problem function. And now we can solve this using gradient descent. And then we have two tricks. One is normalization, right? This is one. The other one here is regularization. Okay. Now, this is basically kind of the whole kind of summary. If you want to have a cheat sheet, this should be there. Again, is this a parametric model? We are trying to find these parameters, theta, W is and weights, and B the ones. And then we have what you were talking about, this basically linear separation hyperplane between the data, right? So now my data looks like this. I have two features, X1 and X2. Then basically, if I can really have a linear separation between them, that's basically where the linear regression comes into the plane. There's another one. I have X1 and X2. I have this linear separation between these two in this case. Okay. Example of how we can set up a problem. I will not really go through detail. You can really go through this at home. So we have kind of this input, and the output will be either positive or negative. We'd like to set up our problem by first deciding on what would be the features in this case. So imagine that somebody tells you that the first feature, how many positive words, the second one, how many negative words, X3 if noise and text, then it's 1, 0 otherwise, and so on. So you can come up with number of features in this case, right? And then you start kind of to start counting and look at the values, and you can start to creating basically the feature vector for your data in this case. And now, although I mean, I'm giving you the solution here, but imagine that somebody will give you basically what the optimal weights, W's and B's in gradient descent, and then you will have basically the value of the output as follows in here. And then the probability of sentiment equal to 1 given the X is equal to 0.67, and the other one, probability of output is 0, is 0.33 in this case. So the output is equal to 1. but we'll go through this with the iris and the MNIST data set in homework number 2 later on. Yes, back to your questions in here. Okay, so the pros and the cons in here. It's simple to implement. It's like just a linear, a linear model that we are looking at. We don't really have any assumption on the feature distribution, right? Or independent or not independent, right? Is most effective when we have a linearly separable data. Like if you look in here, so I have the X1, I have the X2. By nature, basically, there is a very clear line separating them. The logistic regression will work beautiful there in this case. It will really find that line, right? Separating these two. Now, we could use it to have linear separable data, meaning that you can see the red is one class, the green is one class, and now we have a number of these lines, right? So we can really set it up to find these lines, right? We will be able to. But the problem is when we have a linearly non-separable data, right? So you can look at this in here. The only way you can really separate these ones if you have nonlinear, not lines, right? Because remember, the regression we have a line, right? We have lines. So this way method will not really work very well in this case. We will need to figure out, that's where the neural networks come into the play, right? Because it's really trying to find the boundaries between these two linearly non-separable data in here. That's the question you were asking earlier. So these are different applications. Okay, so now one question in the second homework will be, how can the naive Bayes relate to the linear regression, right? The relationship between the two in here. So just a refresher from last time. This is the equation that we used for the Bayes rule, right? The posterior probabilities, probability of y given x, can be basically calculated using the likelihood and the class prior probabilities as we did last time, right? So now, the condition that we had last time was these are equally important. There's no weights, right? Equal weights, and they are conditionally independent, meaning that if I have two features, probability of x1 and x2 given y, can be the product of probability of x1 given y times probability of x2 given y. So now for any number of features I have, the numerator here will be the multiplication of all these probabilities, right? Times the probability of my output equal to whatever the value is, C in this case, right? So now, if my distribution in this case, if I have a normal distribution, a Gaussian distribution, right? So that if I have the probability of x given a y is a Gaussian distribution, then in that case, I can calculate my posterior probabilities. This is the probability of y equal to a C, or 1 in this case, times my Gaussian distribution, over pi p of y equal to 1 times a Gaussian distribution, plus p of y equal to a 0, plus a Gaussian distribution. I can plug in my Gaussian distribution e to the negative, x minus mu1 over my variance. Same thing in here, same thing in here. The only difference between all of these is just basically y and equal to 1 and y equal to a 0 in here. Divide by these quantities, then I will end up with something like this. 1 in the numerator, plus 1 here, and then I have probability of y equal to a 0, probability of y equal to 1, and then I have the Gaussian distribution in this case. If you simplify this, just like it's just calculus, nothing really fancy, then I will end up with something like e to the negative linear combinations, right? So now, if I have a Gaussian distribution in my naive Bayes, and I invoke that they are really independent of each other, then it's nothing but a logistic regression. It really boils down to be a logistic regression algorithm is running, right? So the logistic regression is nothing but a special case of the naive Bayes when I have a Gaussian distribution for my input data, and basically I have an assumption independent feature space or input data in my feature space. Okay, and you will do this in one problem in the second homework. This exactly. So if I were you, I would just mark it because so we never went through this in the class and the solution here. But it's really very important. It's very important special case. Very important special case. And I believe we have also a Python code that you have to run to really verify if this is true or not. But it's a very, very cool solution. Okay. Okay, I think we have 5 minutes. Perfect. Okay. So now what we did so far, I have a 0 and a 1. What if I have a negative 1 and 1? My output could be a negative 1 or 1, not 0 or 1, right? So now let's redraw everything we started with. You remember when I had a single point as my boundary decision, right? So now whatever on the right-hand side will be a 1. Whatever I have on the left-hand side will be a negative 1. Or if I have a two-dimensional, basically I have a line separating them, right? I have on this side of the line, I have the value y is equal to a 1. On the other side of the line, the value of the output will be negative 1, right? So now I need an equation, not only give me a y of 1 and 0, I need something that give me 1 and negative 1, right? So the sigmoid will not do, right? The sigmoid will not do. The sigmoid will give me a 0 and a 1. That's by nature, basically the sigmoid function, remember? 1 over 1 plus e to the negative x. This will map itself to this. Basically, I have a 0 or I have a 1, right? Right? So now the sigmoid will not work in this case. Okay. So let's really model this. So now, one way to model this equation, I have negative 1s and 1s, is the sign function, right? I have the sign of the x, the input. So if the sign is positive, then the output is 1. If the sign is negative, then the output will be negative 1, right? So that could be one function. So now, if I can really model this, I want to model my input using a linear combination of weights, like a weighted average. Then I have the w times the x plus b, or just basically theta times x, right? So now this is my model, right? Again, I'm sticking to the linear model to my feature space, right? So now the difference, before I had this as sigmoid, now I have this as a sign function, right? So now let's look at this more carefully, like this particular sign function. If you look at this sign function, then if it's positive, this is the parameter within the sign function. If it's positive, then the y, basically, if y is positive, then this should be positive and vice versa. This negative 1, this should be negative. So now I can mimic this, or I can really model this. I can write it as I have minus y times theta times x. So 1 as the y times this value, right? And this one is minus times this value, right? I can model this. So I want this one here to be negative, right? Less than a 0. So now, in a way, I could say, I want to find the maximum, right, between two inputs. The 0 is 1, right? And the other expression is this negative y times theta transpose, right? Times x. So now, kind of my cost function to model this will be, which one is the max? Is it the 0 or the negative y theta x is the max in this case? So if you model this, forget about the dashed line for now. Basically, for any negative value for my input, right, it will be all basically equal to a 0, right, until I hit at a 0 value, and then it will start to become basically non-zero value. And it will be positive in this case, right? So all the way from minus infinity until I get a 0, the max is what? A 0. After that, the negative y times theta times x will be the max in this case, right? So this basically will be my cost function. I want to have a cost function, or my cost function will be the green one. And this is basically, it's 0. And then at this point, it will become basically a linear, which is the theta times the x. Any questions about this? Okay. This is called the hinge cost, right? What's the problem with this hinge cost? What is the issue with it? If you want to find the minimum, what do? The derivative equal to a 0. What's the problem with this? You have this singularity in here, right? You have this problem here, right? So that's an issue, right? So that's the problem with the hinge cost in here. This trivial solution at the input equal to a 0, right? So what we do, we basically take the what we call the soft plus, basically nothing but the log of the 1 plus e to the x in this case. This is exactly what it is. You take the log of 1 plus e to the x, it will be this dash line. It kind of mimic the hinge cost at the extremes, but really have a very basically soft soft transition at a 0. So we don't really have a trivial solution at theta equal to a 0 in this case. And that's basically the soft plus function in this case. So now I can remodel basically my cost function as the log of 1 plus e, and then I have basically my input, which is negative y times theta times x, and then I can put really the yi and the xi in this case. Yeah, sorry, this one should be xi yi on the left hand side. This is yes. Yes. We'll look at this. It should be soft plus for now. This should not be soft max for now, right? Because we are really, at the end of the day, we are really maximizing. That's where the soft max comes into the picture. Yes. But for now, it's just the soft plus. But when you maximize it, then the soft max solution. Okay. Okay. Time is done. We'll continue next time. Yes. Question. See it again. Okay, so just quickly before we leave. So this is the difference. The hinge cost is the green plot, the green curve. This is the true one that I have when I have -1 as my classification, my classes output. The problem is that there is a trivial solution, which is the 0 at this point in here. It's not continuous here, right? So I'm trying to model this curve using this function here. As I did before, when I used the log, a negative log, to model basically my sigmoid, right? The same thing in here. I'm trying to really model this using this function here, right? So now this becomes my cost function, right? Which is an estimation of this cost function. This is the true cost function, this one here. But it's really difficult to deal with because of the trivial solution at equal to a 0. This continuity at equal to 0, right? So that's why this is my approximation. And I will revisit this next time on Monday. Okay, thank you.